Have a nice day, everyone. In this presentation, sign recognition with an electronic glove driven by a neural network program on an 8-bit microcontroller, we are going to see how we could put a neural network in an 8-byte microcontroller in a sign recognition electronic glove to help deaf people. I am Felipe Moncada. I will accompany you in this presentation, representing the Embedded System Research Group from UPAO from Peru. This presentation is divided in 4 parts. First, a brief introduction and a previous work review. Then, the proposed research explanation that includes the electronic circuit, the Peruvian Sign Language data, the lookup table-based algorithm, like the reference to enhance, and the neural network. In the third part, we are going to see the results and its validation, and in the fourth part, the conclusions and the future work. Nowadays, we found ourselves in a time where inclusion has taken a very important role in Peru. It is known that 33.8% of disabled people suffer deafness problem. So, in order to alleviate this problem, we developed an electronic glove capable of recognize different signs and translate them to spoken language. Currently exists many solutions for deaf people. Communications, such as vision-based systems or another neural network sensory gloves. But we found that these solutions present weaknesses that we have proposed enhance. For example, the monthly systems are expensive, especially the vision-based ones. Or there are gloves expensive also, which uses professional sensors. In addition, these systems are often big, rough to wear or use in every moment, and others require a smartphone. The main purpose of this work was upgrade a Vaseline lookup algorithm using homemade sensors, cheap and small components, and a neural network to achieve a low-cost prototype with high accuracy and the ability to translate the Peruvian Sign Language. About the electronic circuit, the main component in the circuit is the low-cost 8-bit microcontroller PIC16F8A6, which contains the neural network and only has 8,192 words of memory connected to this. Are the homemade flex sensors. These sensors change its electrical resistance with the bending. It means change of voltages in analog microcontroller inputs that we read later. Also is connected the accelerometer and other components such as resistors, capacitors, and of course, all the circuit is powered by batteries. Well, sign data. In this prototype, we have to recognize the 10 words from Peruvian Sign Language in the picture. We selected those because cover the different combinations available in our design. To develop the lookup algorithm, we use the box plot for each sensor. This graph shows what the range of values for each word is. For example, the index finger flex sensor have this plot where we can see what values it have for each word. We use a value of 0 when we read 0 volts and a value of 1023 when we read 5 volts. We use this type of plot because it shows how scattered are the values that we measure of each sensor. Well, lookup table-based algorithm. This was the first algorithm developed with some like an identifiers that are values given to each sensor. Then, depending on the result, we can know what sign was performed. We sum an identifier if the value of the sensor is below its threshold, for the case of the flex sensor, which has thresholds that indicate if this is flexed or not. For the accelerometer axis is the same but with two thresholds. In the picture on the right, we can see the pseudocode. In a sense, it indicates that first the sensors are read, then these values are compared with each respective threshold. If the conditions satisfy, we sum to a final variable called aux, the corresponding identifier. And the last, we search if this final value corresponds to a signed value. That's why this algorithm is called lookup. The result can also be mathematically expressed with a sum of each identifier in the form of power multiplied with an activator, a variable that could be 1 or 0 depending if the sensor value satisfies or not the condition with the threshold. Neural network. The second algorithm was developed with a neural network. We decided to use this tool because it's very useful with problems such as simulating human gestures, translating hand gestures to speech, and recognizing sign language. However, given our hardware limitations, the main issue was to obtain the maximum accuracy with only 8,192 words of memory, the same that 16.4 kilobytes of memory. The number of neurons in the output layer was fixed to 10, because the number of signs to translate, and the input only 7 neurons, number given by the new number of data channels provided by the glove. We experimented with 10, 5, and 0 neurons in the hidden layer. Regarding to the activation functions, we use softmax function to the output layer and a rectifier linear unit ReLU to the hidden layer. In the picture in the middle, we can see training evolution of the neural network without hidden layer. It achieved an 88.75% of accuracy. It's important to say also that for develop the neural network, we use three groups of data. One group to train the neural network, another to validate, and other to test to evaluate the resulting accuracy. On the left, we can see the pseudocode. Basically consists in read the sensors, then calculate 10 different results, summing the products of each input with their respective assigned weight. Then these results are divided by 1024, that is our analog to digital resolution, to have our results scaled from 0 to 1. And we sum the bias to the division. Finally, we compare and determine what the maximum output is, and it is sent. Measured results and validation. The test and validation accuracy results were compared, and we noticed that the difference in the accuracy between the neural network with 0 neurons in the hidden layer and the neural network with 10 neurons in the hidden layer only were separated by 2.5%. So we realized that was not much problem in the accuracy or hardware limitations. After programming the selected network, we compare its performance with the lookup algorithm performance. We can see in the table on the right that the new accuracy is almost double. The execution time only increased 2.7 milliseconds. This is imperceptible for the user. These are great results except the program memory used that rise 64.8% as a disadvantage. Finally, in the graph below, we can see the accuracy per word for each algorithm. Some words have 100% of recognition, such as mine, water, cat, and suitcase, and others have low level of recognition, like meal, rounding the 58% of recognition. But on the other hand, the lookup algorithm cannot recognize some words even at 1%. This issue is because the homemade sensors generates sometimes scattered values that change one or more bits from the binary value predefined for a word. Concluding, a neural network implemented on an 8-bit microcontroller for recognizing 10 selected signs from Peruvian Sign Language achieved its purpose and yielded a superior accuracy, 88.75% compared with a Vaseline lookup table-based algorithm, 46.25%. As we indicated before, the goal of this project is simplifying the communication with deaf-mute people, with their non-disabled peers, avoiding the need of sign language knowledge. To accomplish this goal, this prototype should be upgraded to recognize more signs with more accuracy. Consequently, as a future work, we evaluate to use alternative neural networks approaches, better hardware, and collect data from a wide variety of subjects. Thanks for your attention.